All right. Okay, so let's start with this idea. Let me get okay, hypothesis testing. The first thing that we know is that, well, let's try a problem directly. And so in this case, we're just finding the area. So this is where you find the z-value. I'll give you the area, and you have to find the z-value. And we've done that. All right. So this is what I had before as everything that has to do with the test, even though the book doesn't show it. I'm putting a little asterisk here. That means it's a test statistic. Okay? So test statistic, the mean for population may be used. So this is a z-test statistic, which I put a little asterisk over it because it's like a z-score otherwise. And then test for the mean population can be used. So n is over 30, and when the population normally distributed, and look, this is known. This is not usually known, but that's what they're saying. So when it is known, you will use it in the equation. When it's not known, you just substitute it for a t-test statistic. It's going to be x bar minus mu over s divided by the square root of n, which is the same as this, except for we change that to s. And we use a different curve of distribution. This is called a t-distribution. Okay? Pennsylvania, the IQ is 100. In Pennsylvania, the average IQ is 101.5, which is normally distributed in a population distribution, a standard deviation of 0.15. So that they're giving the standard deviation. The school superintendent claims that students in her school district have an IQ higher than that. So that's a claim. They just made a claim. This person says our district is higher than average. Okay? So normally you're going to put your claim where? Not in the null, but in the alternative. All right? So let's try it. So it says, she selected a random of 30 students. So n equals 30, correct? And then what we got here, and find the mean of the test score. Test the claim. Now here's a test the claim at what significance level. Okay, so now let's look what happens. First of all, would this be a one-tailed or two-tailed test? Well, it looks to me like it's going to be a one-tailed test because what's happening here is that he wants to know, he's claiming that their IQ is higher. So then you would write the null hypothesis like this. All right? So the null hypothesis is what it is, 101.5. That's the average, right? But what he's really testing is an alternative. Do you see it? The alternative says what? That mu is greater than. So in other words, his district is greater than. He thinks they're smarter. Okay, so now what we're going to do is we're going to calculate the test score. Okay? Now, so what that's going to mean automatically is this. Let me go back to here. Okay, so here's how it will work when you set it up. If you have a hypothesis testing and you're testing the following, that the null, let's say, let's talk about mu, is equal to some kind of number, and the alternative is that it does not equal that number, okay, then you're going to have a two-tailed test. Okay, that's called a two-tailed test. And this is your significance level divided by 2. Alpha divided by 2, okay? If you have this one and you're testing this, that mu is equal to some number asterisk, and the alternative is that mu is greater than asterisk, right? Then you're going to have a one-tailed test. And this one's be to the right. Okay? And all of alpha goes in here, not alpha divided by 2. And what's the next case? Well, same thing. You have the null. Again, you're making a claim that it's asterisk, and then the alternative, which is the one you're really testing, is that it's less than asterisk. Then we're going to have a one-tailed test to the left, right, with all of alpha going in here, not alpha divided by 2. Okay? And when you go in now, when you calculate these guys here, these are going to be called the critical values. There are going to be 2 of them here, right, which are just our z-values. But we have to derive it from how much area is under the curve. So we go from the guts of the table out. And then this one will have 1 critical value here. Okay? And this will have 1 critical value over here. All right? Now we come along with our test statistic. And when we have a test score, or a test that I'm calling like this, depending on which, if we assume that it's normally distributed, then we have x bar minus what we hypothesize it to be, see, divided by, and then we have, in case if we have sigma, then we have this times the square root of 9n. Okay? Now, if that statistics lands here, okay, right in this area here, I'll use a green color, then there seems to be support for the null hypothesis. So this is like an accept. Okay, and these ends are going to be reject. Okay, and now I was saying here, this is going to be reject here, and reject here, and we're going to accept over here. Okay, so it depends how you set up the experiment or the hypothesis test, determines whether it's a one-tail or two-tail. Then in all cases, we're going to have to take a critical value. Then we simply take a look at this test and we ask, does it fall into the green or does it fall into the red? That's all. Same here. We're looking to see where the z-score falls in here or if it falls in here. Same thing over here. We're looking if it falls in here or if it falls in here, where red is the reject of the null. Any questions? Is that too easy? Okay, then let's go on back to the okay, so what kind of tail test is this going to be? Left, right, or both? Look at the alternative. We are right, so it's going to be looking like this. All right, now we're going to look at the significance level. You see the alpha? That's how much area is under the curve. That's the significance we want to make this test. So this is a one tail, right? So now I'm going to say, okay, so this is going to be one tail to the right. So this one tail to the right here, inside here, I'm going to have 0.05. Notice that I didn't divide it by 2. Why didn't I divide it by 2? Why didn't I take alpha and divide it by 2? I got a one tail test. So it's all going in there. Now, let's take a look at the table on your book. And if you look inside the guts, you'll find that you're going to have a critical value of 0.165. What are you going to do? You're going to look in the book, and you're going to know that what you have to do is find that the table is filling up from left to right. You have to find the probability of this on back. Okay? So if this is 0.05, then we have 0.95 under the curve. Correct? Somebody say yeah. So if I get 0.95 and I look in the table, look under your normal curve and look for 0.95, that's inside the table, not on the edge. And when you're inside, go out and you will get 1.65. Why? Because if you look just for 0.05, you're going to get this z-score over here, negative. That's why I had to subtract this from 1 to look where to look in the book to look for 0.95. Because if you look for just 0.05, you'll get the same critical value, but it's going to be on the wrong side. Okay, so this has a critical value here of 1.65. Now, we're going to look at our test statistic. This is the case where sigma is known. So, they tell us that we have, so we have the test statistic, and here's what we claim, 101. That's what we're claiming that's greater than that, right? Our claim is actually in the alternative, see? Claim. Okay, so we put it in there. Now, where did we get the 106 from? We got it from a sample that we took. We took a sample, and I think the sample size was 40 or something like that. Let's see. Right here. No, 30 students. And there says, see, that's 604. Find the mean and test score. So when you find the mean of these 30 guys, this is what your samples is coming out to be, right? So now that's where that number comes from. So now we have what the sample average is, that is X bar, minus what we propose God's truth to be, and then divide by this, right? We got 1.79. Now, let's go back and look at here. Let's see. Okay, look at 1.79. Do you see that test score? Look where it's hitting. It's hitting on this area. Over here, do you see? This area is reject, or there's not enough evidence to support the null. In other words, you're rejecting this, but you're actually proving what you wanted to show. It appears that because you've rejected that the data supports the alternative. And okay, you need to go over that again, or you got it pretty good, or well, we'll do another one. Okay. All right. Okay, here's what I was talking about. From 0.05 on back, there's the 0.95. So we had to look in the table for 0.050. As close as we can get to that, find the z-score, it should be close to 1.65. But 1.79 is where our test statistic hit. Correct? No? It did.
Yes.
And that's in this reject area. Remember, this is accept the null. This is reject the null. But by rejecting the null, you're saying there's sufficient data to support the alternative. Okay. Let's see here. Okay, so let's try another that has a t-distribution. And so the difference is said to be statistically significant. However, when the null hypothesis is rejected, there is always a chance of what we call a type 1 error, or a type 1-2 error. I don't want you to waste a lot of time on this part here, just that you know that if you make a null, if you make a false positive, we're going to call that type 1. If you make a false negative, if it comes out to be false negative, it's type 2, okay? So how you construct an experiment is going to be based in a lot by the actual problem itself. Let's say in the case of President Trump, where he says there's no such thing as global warming, okay? And then you have the scientists that say yes, there is. Okay, there's significant evidence. So I'm just pointing out, but supposing that Trump is wrong, you see the type of cost that a type 1 error would be, because we're talking about human species. It's a huge loss, even if he were, let's suppose he's right. Okay, so he's right. Scientists were wrong. So, but look at the cost. The scientists are just wrong, but we don't have to worry about human species extinction. You see the difference in cost? And that's how you would construct your test accordingly, depending on how important it is to get a to reduce either, because by reducing one, you increase the other. All right, so let's go here. Okay. Okay, so here's the SAT test that you would take for this entry exam. And the average SAT score is 515. And it's telling you it's normally distributed, right? And the population deviation is telling you it's 100. The same superintendent in the previous example wishes to see if the student scores are below average. And she randomly selects 36 students. Here are their scores at 0.011. So what would you have to do? Well, I mean, normally you would have to find the average X bar and S out of that data. Okay, so let's go on to the next. And so they're going to test that this is what the average SAT score is, right? But now in his school district, he's saying he thinks that their SAT score is lower than average. Okay, this is the actual claim. You see that? And so, and they're telling you we want a significance level of 0.10. Now, is this a one-tail or two-tail test? Not all at once. Well, it's only pointing one direction. So it's one, and which direction is it at? Left. That's how easy that is once you get it. So, this is going to be a normally distributed test, and in this case, we're going to have a left-tail test. So we're going to put all our alpha in here, 0.10. Be with me? And we have to find this critical value. If you look inside the table, the normal distribution table, not along the margin, but in the guts, look for as close as you can get to 0.01, and you should get this test statistic. Or you should get this critical value, not test statistic. Right? It should be minus 1.28. Okay? So all in here would be reject, while over here would be accept. Okay? So what do we have to do? The test statistic and see where it lands. All right? Okay or no? All right, so let's see. So let's do our test statistic. Okay. So you first have to compute your average. This is a great problem because you can do it all. And you know, they already gave you the remember 100 was the, they already gave it to you. But we had to calculate X bar. And this is what X bar came out to be, 509 of what? X bar of what? Of the data sample we took. We're taking students from our school to see how, and see what their average is, to compare it to see if, you know, test. So now, this guy here, and I'm going to put a little asterisk over it. So every time I put a little asterisk over it, that is in fact a test statistic. The test statistic is either going to look whether it lands here or here, and you're pretty much done. Okay, so if that thing came out to be minus 0.36, right? Remember, this is centered over 0, correct? So minus 0.36 is, you know, if you're talking about, this is minus 1. So you can see it's pretty close to around here. You see where the test statistic is hitting? You see that it hits to the right of 0.01? I mean, of minus, remember this thing was minus 1 point, what was that, what was our critical value there? Where was it at? Was it here? I can't read it now. Let's see. Oh, well, here. Let's see. Okay, so the critical value is minus 1.28. And this is where the test statistic is hitting. So that means we do not reject the null. But the evidence doesn't support the alternative. You understand? That's our claim. So there is not enough evidence to support that the claim of students is below the national average. You see how they said it? They're just talking about evidence. There's not enough evidence to support the claim that student scores are below the national average. They didn't reject it. They said there's not enough evidence. You can reject a null, but on the alternative, you just say either that the evidence supports it or it doesn't. In this case, it appears that he's not correct. It does not support the fact that they have a lower, whatever, in this case, SAT scores. Okay. Well, here's a situation where, look at this test. We have mu, they're claiming is 24,672, and the alternative, which is really the claim, is that it's not equal to 24,000. So how many tail tests is that? If it's not equal. 1, 2, to the right, to the left. 2. It's 2, because whenever it's not, it's 2. If it's an arrow this way, it's a right tail test over here. If it's an arrow this way, inequality this way, it's a one tail test over here. Correct? Okay, so this is 2 tail. So, let's see if I can come down here. Okay, well, let's just take a look at it. Medical Rehabilitation Foundation reports that the average cost for rehabilitation of a stroke victim is $24,000. To see the average cost of rehabilitation different at a particular hospital, research selects, there's a sample that he drew, n is equal to 35 at the hospital, and finds the average cost of their rehabilitation is $26,343, which is, you know, about $300 less, right? The standard deviation of the population is, so they're giving you the deviation. And alpha, they want a significance level of 0.01. And it can it be concluded that the cost of stroke rehabilitation at a particular hospital is different. Not less, not greater, but not equal to that. So, then we go here. Okay, now, since we have a 2-tail test, right here, this time, I'm going to have to divide alpha in 2. So I'm going to have a 0.05 and a 0.05, you see? And so we have to look at the bell curve table and look for 0.05. Under the table, in this case, you will get, in this area is going to be reject and accept. So if you have to find your critical value, so if you look in the table, I figure you know how to do that by now, and you look up as close as you can to 0.05, you're going to get minus 2.58 for this critical value, which means this is 0.258 for this critical value. And now we simply see where our test statistic is going to land. So now we're going to calculate a test statistic. That's going to go here. Okay? And this, because we know what sigma is, they told us we're using this. And look what we came up with, a value of 3.04. All right? That's our test statistic. So I'm going to do, so that we keep it all on board, I'm going to call any test statistic an asterisk above it. I think they should label it. Now, let's see, where does that fall? See where 3.04 falls? It falls on this side of 2.58, correct? Which is in the reject, right? But by rejecting the null, we're saying the evidence supports his claim, because his claim was put in as the alternative. Exciting? Big stuff here. This is how scientific experimentation goes. You have the data and you see if it supports a hypothesis. We never say we're absolutely correct, but we're correct with a certain probability. So the data either supports, it's better than flipping a coin and making a guess. This is called decision theory. All right, so now, if that's the case, 3.4, then we're going to look over here and see over here. reject since the test value is in the critical region. There's enough evidence to support the claim that the average cost of a particular is different from this, right? Because we rejected the null. By rejecting a null, you say that there's significant, the data, the evidence supports the claim, because we put the claim in as our alternative, right? Not as a null. Okay? So, here's where 0.05 in this area here, these are different areas from here on back. So we now are going to talk about the second way of doing statistics testing, hypothesis testing. What was that? One was called the test statistic, true? And the other one's called the p-value. Okay, now let's learn how the p-value is. The p-value is going to be the area below the test statistic. So let's suppose that we had a test statistic and it came out to be right about here, okay? So if you calculate how much area from here over, right, this area here would be the critical value, right? The critical value here, that's this guy. And then these other guys would be possible places where, you know, the test statistic could hit. So if the test statistic hits in here, I know that the area, the total area in here is 0.01, I mean. Okay, so if the area from this side over, this is my test statistic, so I'll put Z star here, okay? So from Z star over, that number is your p-value. Okay? Get your test statistic, remember the statistic, the star? Calculate the area under the curve on this, all right? So now we don't really have to even calculate a critical value. We just need to calculate the test statistic and find the probability under the curve of the test statistic to the right. Now, how is that going to help us reject or accept? It's going to look like this. Okay, so if the p-value, what is p-value? It's the probability under the curve from the test statistic out, not from the critical value, from wherever our test statistic lands. You find the area from that point on, that's the p-value. Okay, so what I'm saying is that if it looks like this, I'm just going to do this part here, the tail, this is the end part, right? And if this is where Z star hits, that's the test statistic, right? Yes? Okay, then what I'm telling you is that the area under that from the test statistic this way, this area is the p-value. Okay? But remember that the whole area that we're looking for, this is alpha. So all area is, in this case, was 0.01, right? So look what it says. If the p-value is less than alpha, that's a definite reject of the null. If the p-value, this area here, you see this area here? Put it like this. This area. If this area is less than this area, we reject. If the p-value had hit over here, right, then in that case the p-value will have a bigger area, right? Because now it's like, let's say it sits here. Here's my test statistic, right? But let's say that I know that everything under this curve is 0.01. So if I have an area from here out that's less than 0.01, then I'm going to reject. If this p-value were to hit over here on this side of the test statistic, you see that? Then this p-value is going to be greater than alpha. and you will reject the null hypothesis, right? So you have to be able to do it both P and also test statistic, all right? So let's work on some P examples. P-value. Oftentimes when you read in the newspaper, I notice that they don't give test statistic, they give you the P-value. And then you just compare the P-value to the level of significance. And that's what they report. Okay, so let's clear that. All right. So here's how you do it with the P-value method. You're going to state the hypothesis just like we always did. But now you're going to compute a test statistic. That's, remember, the asterisk. And then you're going to find the area, find the p-value. That's going to be the area from the test statistic to the right or to the left. And we'll compare it to alpha. So p-values always are comparing to alpha. All right? So I'm just looking at my p-value to see if it's greater than or less than this. Right? So if alpha is greater than my p-value, that means the area of alpha is more than the area of my p-value, then we reject. And if we have alpha is less than p-value, that means the area from the test statistic back is greater than our alpha, right? Then we accept. Okay? Well, I'll show you some examples. Let's clear that. Okay, let's do some problems. All right. Okay, cost of college tuition. A researcher wants to claim that the average cost of tuition in a 4-year is greater than $57,000. Seems like a good deal. She selected a random of 36 4-year public college students and finds that the mean cost was $5,900. Oh, did I say 57? 5,705. And they give you the deviation. So right away, I'm going to set this up, and they tell you the significance is 0.05. Now, is there support of a claim at 0.05? Use the p-value, okay? So look how they set it up. They're claiming that 5,700. They're saying something the null is, they're saying is equal to 5,700, right? And the alternative is they're saying that the claim is that it's greater than that. So is it a one-tailed test to the left or the right? One-tailed test to the right. See the direction of the inequality? All right. So if we do it like that, then we see that we have this. So all we do is we go straight into, notice I'm not even going to worry about the critical value. I'm going to go straight in and calculate the test statistic. Okay, there it is. 2.28. Okay, that's our test statistic. So I want to do this. So now I got this. All I have to do is this. And I have to just point, where is 2.28? Well, if this is 0, let's say that this is 2.28. Yeah? Okay, and so now I have to find out the probability of here over. Now you can use your z-score from the columns going in. All right, now we know that alpha, the significance that we want to do is we're checking it against 0.05 significance. So I want to see this area from here out. If this area from here out is smaller than that, we reject. If the area from here out is bigger than that, we accept. So I now have to find the area on this thing here. So when you go to your z, with your z table, it's going to tell you the probability of the area under the curve from here on back, which you're going to have to subtract 1 to get this area this way forward. So I'm going to go here, and I'm going to go here. Okay, here's 0.05. So I know that this area from back is 0.05. And I know that my test statistic landed over here, right? Which gives me an area of 0.0113. So you can see that this area is larger than this total area, because this area is from here all the way out. This area is from here all the way out. So which one's bigger? Obviously, the area of the significance, alpha area, is bigger than the statistic area from here on out. Look where it's hitting. This whole thing is reject. Correct? If we would have had an area that was bigger than 0.05, then we accept. Did you see? I didn't have to actually calculate my critical value. I'm just simply looking at the area from this far out compared to the area from the test statistic out. Is anybody following? No. So, let's see if I can do it. All right, so let's try it. Okay, so now we're going to use the p-value to find out whether we support or not. So the claim is equals 8, and the alternative is not. So it's two-tailed. So now, and it tells us we want alpha as a significance level of 0.05. You see that? So I went straight into figuring out what? My test statistic. My test statistic, right? And I find that that's equal to 1.89. So if we take a look at that, and we find the area of this, let's go here. Okay, and then, so, you see this 0.917, right? That is from the test statistic all the way back to minus infinity. That's 97% chance. It's only because the way the book is, the way the table fills up from left to right. So the area to the right, let's see if I can draw that for you. So here we have his like this, you see? And then what we have is the area from here over, the probability, this is the test statistic here. I'm going to put it star, okay? So from here on back, that's 0.9706. That's not what I'm looking for. I'm looking from this way forward. The area under the curve this way. Right? Well, obviously that's going to be 1 minus that. So now I look at 0.0254, and all you have to do now is compare it to the level of significance. Okay, so here's a difference though. When it's a two-tailed test, right? And you have the area of 0.294, that would be the area here under this curve is 0.0294. Okay? Now, in this case, because we have a two-tailed test, we're going to double the p-value. So because it's two tests, you're going to take twice this area. This will only be the case of two-tailed, because we're going to put it all under there, and it came out to 0.518. So all you have to do now is compare this value to the alpha value. What they're saying our alpha value was, 0.05, and ask which one is bigger. So let's see. Okay, so here we have the area from here on out. You see, 0.025, it's half. And here's the other half, because it's two-tailed, right? So now I find the area from here on out. Okay, this is the point where we hit our test statistic. And the area from here on out is 0.0294. And the area of the here on out, sorry, this is 0.025. So which is bigger? Well, clearly the area from here on out is bigger than the area from here on out. Yes? And over here, the area from here on out is bigger than the area from here on out. So, do we accept or reject? Well, what's bigger? Is alpha bigger than the area under the p-value? This is the p-value. This is the area. That's not the p-value. Here's the p-value of 0.2. So in this case, the p-value is greater than our alpha than our area than our p-value. You see that? The area from here out is greater, and obviously you see that it's sitting in the accept range. This is the test statistic. All you're doing is comparing the area from the test statistic back from the significance level back. That's all. Yeah, or you could calculate the critical value and see where it hits, if it hits on this side or this side of the significance level. Okay, let's try it in action. Okay, so here's a general rule. If the p-value is less than 0.01, because we haven't been using any significant letter significance below that. You could, but we don't. Then reject the null. If p-value is less than 0.01, that means less area on the tail than this value. Okay? If the p-value is greater than 1, but the p-value is less than 0.05, that's sort of a middle term, then we say reject the null. Okay? And finally, if you have a p-value that's greater than 0.10, do not reject the null. So we have two methods. We have the test statistic method, and we have the p-value method of checking whether a null hypothesis or a claim is accepted or not. So here we have table F, which is our t-distribution. Our t-distribution requires degrees of freedom. Degrees of freedom is 1 minus the sample size. Okay? So find the critical value for alpha. Yeah, so here's alpha with a degree of freedom of 16. So I go to 16 on your t table, on your t-distribution. And that tells me 1.76. So that is the area, that is the test statistic. Now I need to know the area from this side out. Okay, so I go over, let's see if we get here. Oh, I missed it. Okay, go up here. Let's go. Okay, now, when we use the t-distribution, we're going to use this as our test statistic. Okay? Somebody say yeah. Okay, that's our test statistic. Just like everything we did before, except we're using the t-table distribution. Okay, and everything else is the same. So let's do it real quick here. Okay, so degrees of freedom, well, whatever, it's just a roundup thing. So this is now going to be our t-values, degree of freedom. And so the critical value for the alpha with degree of freedom. Okay, find that critical value, and then find the area under the, well, compare it to the significance level. Let's try one so we can see it. All right, hospital infection. Hospital is a dangerous place. It really is. It has some bacteria there that are super strong, called MRSA. It's one of them. You don't want to be in there. You certainly don't want to take young kids inside. Okay, a medical investigation claims that the average number of infections per week in Pennsylvania is 16.3. That's the average. But there's going to be a claim. A random sample of 10, and this 10 has a mean of 17.7 infections. The sample standard deviation they're giving you, 1.8. There's enough, is there enough evidence to reject the investigator's claim that alpha equals 0.05? This means two-tailed test, right? And then in this case they put the claim up here. They're saying that. Okay, so now let's find the critical values are 0.2 and 0.2958. That's because we have an alpha of 0.05, right? So when we have a two-tailed test, let's see if they have it here. Okay, and here's your test statistic for t-distribution. Notice that we're using S instead of sigma. When we use S instead of sigma, we're doing, but you're using the t-distribution. And this again, so now all I need to do is find the area from this farm out, and that will be my p-value. And I will compare it to my significance level. That's it. It takes a little while to grab a hold of it, but it's really not too bad. Once you, let's see if this thing okay. So 2.48, now we go here. Remember the significance level. We had a significance level of 0.05. So we go here. Okay, now, notice what we did. we divided the 0.05 as usual by 2. So we have 0.025 this way and 0.025 this way. Yes? That's our significance level. Now, our test statistic hit right here. So all I have to do is find out, where the test statistic hit. I find this area out and compare it to 0.05, and that will tell me whether there's enough evidence to reject the claim. We're on the reject side, correct? So we're rejecting the null. And so there's enough evidence to reject the claim that the average number of infections is 16.3. Now, that one was using the test statistic, didn't we? This is the critical value because we have 0.05. Remember that we divided, so this whole area from here on out is 0.025. And I really have to do it because this is using the test statistic, and this is my t-test statistic right here, and it's landing at 2.456, which is clearly in the rejection area. Yes? Okay. You can see then, I'm going to just go over, there's one more thing to go over, and then we'll be done with 8 as far as test statistics are concerned. So, what do we have left to do? We have left to do the test hypothesis about the proportion. Remember p-hat? Does anybody remember it? P-hat proportion? That says, okay, that's another one. Degrees of freedom. Let's see. This is another t-distribution. Test statistic. Alpha is 0.05. This is a right tail to the right. A tail to the right. One tail to the right. And let's see. There it is. Test for proportion. This is going to be your test statistics when we're talking about proportion. And so right here, asterisk, meaning that's our test statistics, right? And this is our sample proportion, x over n. That's p-hat. X from our sample, the number of x's that were in that category divided by n. P is the true population proportion, and n is the sample size. Okay, I know it's getting exciting. So, if you're going to use a test statistic, you're going to do exactly the same thing. You're going to go here. This is how you're going to test the test statistic. All right. Here is obese young people. They're saying that the proportion is 0.75, and from their sample, they're saying it's not 0.75. See it? Significance levels are 0.05. So, if it's 0.05, do we have a two-tail? Yeah, we do have a two-tail. So we're going to put half of this 0.025 on one side and 0.025, and we're going to get critical values of 1.96. Now, we'll calculate the test statistic. Now we calculate, there's 1.96, and there's 1.96. We calculate the test statistic I showed you with the test statistic that looks like this. Yeah, proportion. There it is, test statistic. You take your p-hat minus the p cubed divided by n. That's your test statistic. And we're going to see where that lands. In this case, it lands over here. You see it? 1.65, 1.51. That's in the accept area. You got it? Okay, and then the last one. Oh, is it? Okay, so the last one is just going to be, the last one's going to be about sigma, and we'll be ready for chapter 9. Any questions? I'll be going over some of this stuff at lab. Any of you that have a question can welcome to stay.